This is going to tackle the most basic point, which is the motivation for the concept of the entropy of a probability distribution. So we're going to justify the entropy in terms of the expected number of symbols it takes to record a sample from a probability distribution. That the technical content will be summarized as Shannon's source coding theorem, so that's where we're working towards. And then as a result of understanding that, we'll be able to see what the meaning of the KL divergence is, at least from the point of view of information theory. There are other ways to motivate it, but today I want to focus on the motivation which comes from this kind of point of view of signals and information and so on. Okay, so the setup is the following. So we're going to consider an observer receiving or measuring signals or samples from some set X. And for simplicity, I'm going to assume X is finite. I'm not going to say it's completely trivial to justify in the way I'm about to the infinite case, because actually I don't know completely how to justify it. You can extend the formal definition of the entropy trivially to the general case, but the motivation seems a little trickier to me. Anyway, today we're going to assume that X is finite. The signals or samples are distributed according to some probability distribution Q. Which is assumed unknown, as usual. Okay, so usually in this seminar we would then proceed to say, okay, the problem is to try and infer what that distribution is, or what the process which generates it is, by formulating a model and then talking about which models are better than which other models and inferring parameters and so on. Today we're going to go in a somewhat different direction. So rather than modeling the true distribution, we're going to start with a much more basic problem. And the basic problem is, well, before we can model something, we have to be able to write down the information that we've received. So how do we store the information? Of these signals that we're receiving from this source? Okay, so my cartoon is going to be the following. So here's you sitting at a desk, and you're lucky because out the window are a collection of beautiful, colorful birds. The reason I'm choosing color is that you have to actually make a choice of how to encode this, right? So here's your birdies sitting on the tree. And you want to maybe talk about or think about, well, what is the most likely kind of color for a bird? Okay, so these colors are there's some distribution out there in nature over the color of birds. We're going to assume, and you, by the nature of your perception, sort of have to take as a starting point the idea that maybe you can divide up these colors in some discrete way, not necessarily finite. And then you're going to write down what those observations are, right? So maybe you're going to decide to record red as 0, 1, and blue as 1, 1, and green as 0, 0. Or something like that. So you get the idea. But these are choices, right? There's a choice of alphabet here. In this case, it's sort of implicitly 0 and 1. There's a choice of which sequence of symbols in that alphabet to associate to which observation or which signal. And then you can ask questions about, well, which encodings are better according to some criteria. All right. So I guess we could imagine a variety of different kinds of situations. Maybe in this, as in this case, what comes to us is not something that's already in a natural alphabet, say a color. Although we could use English, right? We could write down red, blue, and green. So we already have we're sort of already predisposed to use a particular alphabet, the English alphabet, and a particular encoding of these observations into that alphabet. But maybe you could imagine a measurement or a signal that doesn't say a chunk of a wave file or some sound that comes to you. I shouldn't say a wave file, it's already encoded. Suppose a chunk of audio, a bird's song. You don't have some already defined alphabet and encoding of that to consider. So that's one situation. You don't already know an encoding. But you could also consider a situation where you know an encoding, but you might think that it's wasteful. Right? So in this case, if red, blue, and green are the only colors that appear in nature, well, I'm using 3 symbols to write down red, and 4 symbols to write down blue, and 5 for green. But the encoding I have on the first board is cheaper, right? It uses less symbols, and the alphabet is smaller. So in some sense, you could imagine that that's a better encoding. So what we're going to be investigating is the optimal encoding where the criteria is that shorter is better.
Hey, Dan.
Yeah.
You said this is kind of a step that you have to be able to do before modeling. Is that just like, you mean that colloquially, or you mean this is like somehow different from modeling? Because I've also seen people say that compression and coding is just modeling.
Yeah, I don't know how to draw a very sharp line between them, so I'm not really asserting that. I'm not asserting really any connection between them, except that it does seem to be clearly, at least from a practical point of view, a necessary initial step. I mean, you can't. Well, maybe operationally it's an initial step. I don't know that mathematically you have to worry about this before you start talking about models.
Okay.
Okay, so what is the best encoding of signals? Where best is going to mean shortest. Why shortest? Well, I'll come back to that in a minute, but let's just set up some terms first. So we're going to suppose, given the alphabet, so which is a non-empty finite set. And by sigma star, we're going to mean non-empty sequences in sigma. Usually this means arbitrary sequences, but for today, I don't want to count the empty string. I'm also going to assume that there are no signals x for which the probability is either 0 or 1, and sometimes it's convenient to allow the empty string for technical reasons if you want to encode events that have 0 probability and edge things like that, but it's not that interesting. I'm just going to skip over that kind of thing. We mean non-empty sequences in sigma, and as usual, if I have a sequence, its length is going to be denoted by these bars. Right, so definition. What do I mean by an encoding? So an encoding is an assignment of a sequence of symbols to any signal in a way that assigns distinct sequences to distinct symbols. Right. Now, it's a reasonable hypothesis that the use of resources in storing the information in a signal is proportional to the length. Now that gets into a bit tricky territory, but you could say sort of at the limit you need to at least erase a certain number of squares or positions in order to store a symbol in the alphabet, and that'll be proportional to the number of symbols you're storing. So this is a sort of reasonable hypothesis. And then by best I'm going to mean the fewest use of resources. And therefore, since that's proportional to the length, what we want to do is take the shortest. But for what? I mean, for all x, or do some x, are they more important to shorten than others? So that's the next point I'm going to make. I suppose it should be pretty obvious that not all x's are created equal. If we are concerned with receiving multiple signals from our source and then encoding them and writing them down, it's much more important to get a short encoding for more common sequences, because those will save us more resources over many samples. Okay, so let me just make that point more precisely. So the resource cost of storing n samples i.e. signals received, is by my hypothesis proportional to that, obviously. Okay, which I'll just rewrite in a pretty obvious way. Okay, so that's just sum over x, px times mx, where px is the empirical probability according to my samples. And by this I mean the Kronecker delta, right? So 1 if x equals xi, 0 otherwise. So I've got my n samples, and this is how much, how long the stored information is. Okay, so
Dan,
yeah.
Is this like cost?
I can't really hear you, sorry.
Right, can you hear me now?
Yep.
Is this some kind of expected cost?
Well, right now I'm writing down the cost for this particular sample.
Oh, right.
But yes, that's right. I mean, when I...
But there was... But how come there was a probability that got introduced, right?
I said empirical probability.
Oh, empirical probability just means the proportion of the sample.
That's right.
Yeah, sure.
Yeah.
Okay.
I see a question in the chat. Was that what you asked me earlier? storing information and modeling information.
Yeah.
Yeah, I guess that's an interesting question we can come back to. Okay. So for n large, this converges to just the expected value of this random variable, which is the length of the encoding. Okay, so if we want to do a good job of storing samples or signals from this source, what we want to do is choose an encoding M which minimizes this expectation. So we have an optimization problem. Which is to minimize this quantity over all possible encodings. Okay, so we're going to solve this problem. Well, we're going to figure out as best as it's possible to do what the value of u is, sort of as a function of q of x. It'll take some time, so we're going to first produce a lower bound and then an upper bound, and the eventual statement will be in terms of blocks of messages in the limit as the block size goes to infinity, and that's the Shannon source coding theorem. But before that, I think it's worth just staring at this for a minute and thinking about how we would do this in the cases where this is easy. Okay, so what's an example of a case where it's easy to find an optimal encoding, an encoding that minimizes this quantity? Well, if there are fewer possibilities than there are things in our alphabet, we just get to assign. I mean, obviously I want to take the lengths of the encodings as short as possible, right? And the shortest possible thing I can give is length 1. That is, I just pick a symbol actually in sigma for every event. So, you know, so if x is red, green, and blue birds, and I literally have 3 distinct symbols in my alphabet, then I can just get away with m always being of length 1. And that's as small as I can make it. Okay, so then it's easy. What if there's one more thing, one more possible signal than there are things in my alphabet? So I have to pick one of them to be encoded by a length 2 string rather than a length 1 string. Well, it's pretty clear that I can make that optimal by choosing the thing that gets the length 2 string to be among the least likely things. Right, so that then when I look at this sum, in the case where this is a 2, this is smallest. Does that make sense? Okay.
Yeah.
Then you might go one case beyond that and think about, well, what if there are 2 things I have to give length 2 to? Well, you should pick them to be, you know, the smallest probability things. But you can sort of see if you start thinking about it that it's quickly going to become a bit of a difficult sort of trade-off, right? If you've got to choose between multiple things and, you know, which ones to bump up to longer length and so on. Okay, so this is not a trivial problem. I wouldn't say it's very difficult. We'll be done with the proof by the end of this seminar, but it's not obvious how to come up with an optimal encoding. And the most non-trivial step is to reformulate the sort of parameterization here to figure out what are the possible length functions for encodings. So that's my next. Let's call the craft. Macmillan theorem. Whoa. Okay, so we're going to construct lower bounds for u. Lower and upper bounds for this quantity u. Okay, so the first observation is that if you have an encoding m which produces the same lengths as an encoding m prime for all signals, yeah, I guess I wanted to introduce some notation. It's a bit of a pity it's on the other board set, but I'm going to call this quantity here um.
Sorry, Dan, you said if the size of x is smaller than the size of sigma, and then you didn't write anything.
Oh, I didn't write anything. Yeah.
Say that.
Then any m with mx always equal to 1 gives a minimal encoding, i.e.
Thank you.
um is minimal. Yeah, thanks. Okay, I think I'll reproduce the over here. So side means sum over x in x, qx, mx. Alright, so if an encoding assigns the same lengths, maybe different sequences of symbols, but they all have the same length for each input, then is equal to prime, as is obvious from the formula. Hence, this quantity u, which we're interested in, is the minimum. You can think about it as the minimum over length functions. Right, so from any encoding you can derive a length function. I'm writing it as just bar m here. I hope that's clear. So Lx stands for this. Any encoding determines a length function, and well, the quantity here that we're minimizing is only depends on the length function. So this is the same. All right, well, the reason this is useful is we can characterize which functions taking values in positive integers are length functions of some encoding. That question is answered by the following theorem. I won't have time to present it. Actually, I think it would be a good idea for somebody here to prepare a talk on this, because it's actually not, in my opinion, it's not possible to really understand the meaning of the KL divergence until you understand what I'm explaining today, plus how this procedure of constructing an encoding from a length function works. That's at least that's how I tend to think about it. Okay, so given a function, there exists an encoding for which it is the length function. If and only if Oh, cool. If and only if the sum over x in x. Yeah, the proof isn't difficult. It's a bit too long to give in this talk, but I think it's instructive to see. Okay, so you're given a function L. It comes from an encoding if and only if this inequality holds. So let's just think about this as a kind of sanity check for a second. If you make Lx larger, this is going to get smaller, right? So what's the constraint here? Well, suppose, I mean, it should be easy for L to be the length function of an encoding if L assigns very large numbers to things, right? If L assigns very large numbers for things, then you can clearly fit, I mean, relative to the size of x, you should be able to fit x into that set of symbols of things with that length. And that tracks with the formula, right? If Lx is very large relative to the size of x, then somehow the left-hand side is going to be easily less than 1. The constraint becomes tricky if you try and make the Lx's small. Making them small makes the sum ends on the left large, and somehow you have to fit them in to 1. So that sort of makes sense. Okay, I'm going to suppose in all the rest. I'm not saying this is necessary in this theorem, but I'm remembering it now, so I'm going to suppose that the probabilities of all these signals are in 0, 1. Otherwise, in some of the following, I'll have to make some special cases. Okay. And that basically comes by, you can prove this by thinking about encoding things in terms of trees. Okay, so to come back to our original calculation, so U was the minimum over these sums where L satisfies this constraint. Okay, now I'm going to do some operations to the right-hand side, and it will turn into an inequality. Okay, so what I'm going to do now is relax the class of functions. So let x be real valued. Same constraint. Now the point here is that this is a bigger set than this, so its minimum must be smaller. Okay. Now I want to argue that I can replace this by an equality. Now what I'm going to do in a moment, as you probably already guessed, is to use a Lagrange multiplier argument. You could probably do it already here with the more sophisticated versions that handle inequalities. In this case, it's easy enough to turn this into an equality and then use the simplest form of a Lagrange multiplier. So we'll just do that. Okay, so first it's worth observing that this minimum is actually achieved. Let me think for a moment. I'm not completely sure I actually need this. Well, okay, since x is finite, we can bound UL. So this quantity is UL, right? That's a definition. I guess I was writing UM before. So we can bound UL below by UL prime for some L prime that takes values in an interval. The reason I can take it to be non-negative, you can just think about what would happen if it had a negative value and just shifting it up by a little bit. And I can take it to be bounded above by a constant c that doesn't depend on L. Yeah, it's kind of easier to think about yourself than for me to argue for it. Since x is finite, and if you think about the size of sigma, you can convince yourself that if the values of L are bigger than, you can come up with a constant such that they're bigger than that constant, you can always safely decrease them by some amount and maintain that inequality. Okay, so that's not so important. So we can replace the minimum over all functions from x to r by a minimum which only considers functions L taking values in some bounded interval. Okay, the point being that that's compact. So the minimum is actually achieved by some L star. I mean, I guess I could have done this part when I made this first step, right, rather than going to R first. Anyway, so since this is compact, the minimum is achieved by some L star. Now, suppose I want to claim that this L star actually makes this constraint an equality. So suppose for a contradiction that, what am I writing? That L star makes this a strict inequality. Okay, you can see that all the L stars must be positive. Again, maybe I'll leave you to think about that. So that means that I can pick one and decrease it by some amount sufficiently small, and decreasing it will make that term larger in the sum, but because I decreased it by a sufficiently small amount, I'll still be strictly less than 1 because I'm bounded away from 1. But that then contradicts minimality. Okay, that means that this minimal guy actually makes this an equality. So we can conclude that... Sorry,
why can you decrease it slightly?
Yeah, so if it's positive, I can decrease it and still keep it away from 0. And the point is that when I come here, so each of the terms looks like this, right? So if I decrease that exponent, I'm going to make the denominator there smaller, which makes the fraction larger, which could in principle break this strict inequality, right? I mean, if it was less than or equals to, it might, but since it's a strict inequality, there's always some gap there, and if I give myself an epsilon, I can choose the delta in the size of the decrease here to keep it within that epsilon so that it's still less than 1. Does that make sense?
Okay.
Yeah.
Thanks.
Okay. That means that in the previous line where I minimized over things satisfying the inequality, I can now minimize over things that satisfy the equality. And I could put my compact interval here again, but I don't care anymore. Okay, so that's the first. There's sort of two steps that have happened here. The first was to apply Macmillan, and the second was to switch from the inequality to an equality. I guess you could say we also relaxed it to consider functions L that don't return integers. And all of these are part of, I mean, at least this relaxation to not allow integers is part of the reason why it's a little difficult to think about the content of the entropy. But we'll come back to that. Okay, well, now we've got something we can formulate as a Lagrange multiplier problem. Okay, so we've got an optimization problem subject to a constraint. I'm going to simplify things a little bit by setting up some notation, but I think I'm out of boards here, so we're going to move over to the second. Yeah, we'll move over here and continue. Yeah, that's right, Matt. It's the it's a tree with branching factor sigma, exactly. Okay, so maybe I'll just repeat this. Okay, so we're going to set s of x to be the thing in the constraint. So we're basically going to change variables from L of x to s of x. Okay, so L of x is minus log s of x, in which case I'm continuing from here. That is equal to the minimum of just substituting this into here. Minimum of minus sum over x q of x log sigma s of x subject to this. So that's max So it's not clear we should think about the current optimization problems having anything to do with an encoding, right? Because these L's may not be integers. They don't necessarily come from an encoding anymore. This constraint that we've set up is an analog of what's in the Macmillan theorem in order for this to be a lower bound on the thing we care about, but we're not assigning any particular interpretation to the optimal function L in the current situation. Okay, so what do? We're going to introduce Lagrange multiplier lambda and set L as a function of S and lambda to be the thing we're trying to maximize rather. Plus lambda times the constraint. So we have as many variables plus 1 as there are x's in x, right? So for each x we have a variable sx here, and those derivatives are qx on sx log sigma plus lambda and this one here. Okay, so where are all those partial derivatives? 0. Well, we're going to look at the first equation first. Well, I guess the second one is easier. Those all have to add to 1. Don't think about them as probabilities, right? Because, well, I guess it is appropriate to think about them as probabilities, isn't it? Those are non-negative. The first equation gives rearranging for Sx here gives minus Qx on lambda log sigma. Okay, substituting 2 into 1. Gives that the sum over x in x of minus Qx lambda log sigma has to be equal to 1. Therefore, minus sum over x in x Qx is equal to lambda log sigma. I guess we better know lambda is positive before we do that. Sorry, I mean lambda is non-zero. Yeah, but that's true. Okay, but this is 1, right? So therefore lambda is equal to minus 1 on log sigma. Which now substituting back in here gives us Sx is equal to Qx. This is what we were looking for. So this shows that there's a unique solution, a unique critical point of L. I mean, then technically speaking, you have to check that that actually is the global minimum of your original optimization problem, but you can do that. So this shows that the original optimization problem on the first board here has the solution S, where Sx is equal to Qx. And in the original coordinates, so L must be equal to minus log sigma Qx. Okay, so now we basically have our lower bound. Right, so u is greater than or equal to, well, the minimum that I formulated as a maximum, which is, by what I just performed, equal to the following quantity, the sum over x in x, Qx, times Lx. Lx is minus log sigma Qx. So this is minus sum over x in x, Qx log sigma Qx. Okay, so this quantity, which is appearing here for the first time, is called the entropy, HQ of Q. Usually you'd take sigma to be in some other base. Doesn't matter, of course, up to a multiplicative constant, so we'll just stick with this. Okay, so it's with respect to sigma. I guess it's not clear if I took the minus sign in there. I intend to have the minus sign. Okay, so just to recap. So U was the minimum of all encodings of signals from our source into strings in the alphabet sigma of the expected length of those encodings. And we've shown that that's bounded below by the entropy. Next, we've got to do an upper bound and then kind of talk about how to somehow get that upper bound and lower bound to approach one another. But are there any questions about this first part? Note that although U was talking about encodings, right, and therefore the things that were the expected value was of lengths, right? So it was sum over qx, sum over x, qx, and some length. Here, the thing that it looks a bit like this, but the length now is. I mean, we could change this to 1 over qx. Maybe that makes it even less. Makes it less unlike a length. I mean, U was turned in things that was something like sum over x, qx, mx, right? So it's sort of clear we're supposed to think of this quantity as being somehow related to this. But, well, there's no reason for that logarithm to be an integer. Okay. All right.
Dan, have you heard about arithmetic coding?
No.
Okay, we studied this in second year algorithms. This is the technique by which you can use discrete symbols and achieve an amortized code length that's not an integer for particular symbols.
That's right. That's what I'm about to explain. Yeah.
Oh, okay.
Well, I won't explain it. I'll kind of leave it. It's implicit in the way we're going to deal with the limit as we consider sequences of signals. I guess that's what you mean by amortized.
Yeah, something like that.
Cool. Yeah, I didn't know the name. Thanks. Yeah, it's a neat idea. Kind of. All right, for an upper bound. Okay, so just to recall, U was the minimum. Well, it's kind of easy to construct an upper bound, right? I just have to find something in the right-hand side. Okay, well, given what I just discussed, there's a kind of natural thing to try, right? Maybe that logarithm is not an integer, but if I take the closest larger integer, then maybe that will work. So that's what we're going to do. So I'm going to set Lx to be, and here now I'm back to this situation, right? This was the original thing where the L took values in integers. And I'm going to take the logarithm and take the roof. And that's going to be a non-negative integer by the way I've set things up. Then, well, by definition, this is greater than or equal to that logarithm. Okay. So that's an integer valued function which satisfies the hypotheses of the Macmillan theorem, and therefore we get our upper bound. Hence, u is less than or equal to, well, I guess maybe I'll do it on the next board. Okay, so u for this particular L, right, because this L is in the set and u is the minimum of these quantities over all such L's in the set. But Lx was the roof, and the roof is less than or equal to the quantity plus 1. So I'm just expanding that. And this gives us a sum over Qx, which is just 1. Okay, so that's HQ plus 1. Okay, so what we've proven so far is that with the above notation, the entropy of Q is less than or equal to this minimum expected length of the encoding of a signal. And it's bounded above by the entropy plus 1. Okay, so you can start to see what the entropy is trying to tell you. We're not quite finished because, well, there's this gap of 1, right? It's not really satisfactory, but it's pretty obvious that if you instead talk about the expected length of encoding a sequence of signals from the same source, that roughly speaking you're going to get this 1 into a 1 over b, where the b is the length of the sequence. So that's what I'll now explain. Yeah, any questions up to here? Comments? Okay, so this is pretty straightforward, so I'll be a little quick. A block of signals is just a sequence of IID samples. From Q. I guess there's one observation, which is that when you minimize the length of a stored, well, I'll say it precisely. Okay, so given an encoding, I'm going to write this to just mean, I guess there's a little bit of a tricky point here to do with prefix free things, right? So I get a sequence of signals from the source, I can encode each of them and then just write them down, and that will have length, the sum of the lengths, as long as I don't need any punctuation, right? If there's punctuation involved, like a comma or a space, it seems like I might have to add a b-1 or something here. I guess you could probably do that and not change the conclusion I'm about to make. I didn't check, but in the limit it probably goes away. But you can also avoid it, and probably this is more standard, by assuming that M is a prefix-free code, so that you don't need spaces or punctuation symbols when you write down a sequence of encodings. But maybe that's a topic for another time. All right, so you then look at the expected length of writing down a sequence of IID samples from the source. That's this quantity. And an easy calculation will convince you that that's b times the expected number of symbols required to write down a single sample. Right, um was sum over x, qx, mx. Okay, so hence the point here is that the minimization over encoding blocks is just related to the minimization of encoding single signals. Right, so let me call it UB. That's the minimum over all encodings. I guess I didn't think about the possibility that you could have an encoding for blocks that somehow worked better than using the same encoding for each sample, but since they're IID, I guess you could argue that's not possible. Right, so this would be the best you can do for encoding blocks, but by what we just said, I mean this quantity here is underline, right? But what we just said, this is b min over m which is bu. Okay, so now we're ready for the source coding theorem. So colloquially it says the minimum number of symbols per signal and in expectation to encode a block of B signals from Qx, that's a function of B, converges to HQ as B goes to infinity. Proof. Okay, what I mean is 1 over B UB converges to HQ. UB is on the previous board. Well, but UB is BU, and I had these upper and lower bounds for U, so just multiplying them by B gives me this. And therefore HQ sorry, there's a 1 there. Wait. No, I've done something wrong here.
Doesn't the 1 over B just go away?
Yeah, I'm a bit confused actually. So I had this, right? A UB is BU.
Oh.
Wait. I mean, I can't just multiply through by B. This doesn't help me, right? This gives me that. Wait.
What if you... Can you put UB equals BU into the limit equation that you have?
Just a second. Yeah. Yeah, what was the suggestion, sorry?
Can you put the can you put UB equals BU into this? So if you replace that with BU, then you end up with U converges to HQ. But U is just a constant, so you get U equals
Yeah,
HQ.
so I must have screwed something up here somewhere. I mean, I can just apply everything I said before to get this, but with a 1 here. Yeah, I thought I didn't need to do that. Okay, it's a bit unfortunate that I'll have to just sketch this argument now. I think from what I've got on the boards here, it's not actually. Okay, so I'll explain how I can get to this formula directly. I thought I did a cleverer thing, but appears not. Okay, so what I want is this. You'll agree that if I can prove that, then I divide through by b and I take the limit and I'm done, right? Okay, so why is that? Well, look at this. I can just solve the optimization problem again, but for this, you see. Okay, so look at this optimization problem. The sum on the right-hand side, unfortunately, it's in here. But the sum on the right-hand side, basically you can treat the components separately. And so you can set up this optimization problem just for each signal separately, basically, and then solve it as I did before, and you'll just end up with BHQ. And for the same reasons as before, you'll have a 1 there.
Oh, right.
Yeah, so that's... I'm sorry I have to finish in this kind of soft way, but that does work. And so then you end up with this formula here. I think there should be a way of deriving it from what I said, but I don't really want to mess around with it too much right now. Okay, so therefore...
No, this makes sense.
Sorry?
This makes sense.
Yeah. That was how I originally did it, and then I switched it to this. But okay, so that's quite satisfactory, right? So this quantity, the entropy that depends on the true distribution, tells you that you can't do better than storing this many symbols per signal in expectation when you consider blocks and the block length goes to infinity. I guess I'm a bit over time already, but it's really only a few more minutes to explain the KL divergence from here, so I'll do that over here. Okay, so that tells you the meaning, the information theoretic meaning of the entropy of a distribution. It's about an observer receiving signals or samples from the distribution and trying to write them down. And how many symbols do they need to do that? Okay, so here's how that relates to the KL divergence. Okay, suppose you, or the observer, this is going to be a bit sketchy because it's not completely straightforward to think through completely. But suppose the observer believes the source has distribution px rather than qx. Okay, so what do I mean? What does it mean to believe the source has distribution px? Well, if you think you know the distribution of the signals, you can take what we just discussed and kind of operationalize it and turn it into a means of constructing and encoding. Right, so that's sort of in the proof of the Kraft-Macmillan theorem, right? The Kraft-Macmillan theorem, if you think back through what we just discussed, to prove the upper bound, I said, okay, take as the lengths these logarithms of 1 over qx, and take the roof. That's an integer. That satisfies some constraints, and the Kraft-Macmillan theorem, it's constructive. It tells you how to construct an encoding which has those as its lengths. Okay, so to believe the source has distribution px is to take the roof of log px, get an encoding that has those integers, and use it. When somebody gives you a sample from the signal, use that encoding to write it down. Now that's a roof and not really the logarithm itself, but that's sort of relevant to what Matt was saying. As the length of the blocks goes to infinity, you can sort of do better and better with that roof, and it gets closer to the actual logarithm. So roughly speaking, you can think about actually using an encoding which has the length which is minus the log of px. All right, so that's the part that where there's a bit more thought really required to convince yourself. But I'll just say for today that employing the Kraft-Macmillan theorem, what did you call it, Matt? Arithmetic encoding? So,
yeah, arithmetic
coding. Okay, employing the Kraft-Macmillan theorem, construct an encoding, and I'll just say with in scare quotes, because this need not be an integer, right? So it's not. Okay, but that's the idea.
So this isn't a proof of the Kraft-Macmillan theorem?
The proof will actually construct an encoding for you, given the integers Lx. Yeah.
Okay. Oh, that's why you're saying we should read the proof.
Yeah, I think it's interesting. Yeah.
Okay. Cool.
Okay. Now, putting aside the difference between this and an integer and so on, and just sort of thinking in the limit as b goes to infinity, they think this is optimal, right? So they think all that we've done guarantees them that this is the best way to write down signals, any encoding that is produced by this procedure. Okay, so they think this is optimal. But in fact, you can achieve a lower sort of symbol rate. You can achieve a lower per signal symbol cost, or just like the number of symbols in expectation, by actually knowing Q. So roughly speaking, you have P, but that's different to Q. So there's some X's for which you think they're likely, and Q in reality they're a little bit less likely or a little bit more likely, which means that you're a bit off in how you assign your encoding, at least. And you can see how this probably shouldn't show up necessarily for single signals, right? if there's a very small gap between the probabilities. You'll only see it if you take sequences. Okay, so you can do better if you use the actual true distribution. Okay, so there's three quantities that we're sort of implicitly talking about here. Sum over x, qx, log 1 over px. All the logarithms are base. Okay, so this is what you actually get. I mean, remember, we're sort of thinking about this as length of encoding, right? Modulo the caveats I discussed. So this is the expected number of symbols per signal that you actually get. So you're getting a signal, you write it down. You're getting a signal, you write it down. And what you will calculate as your empirical estimate of how many symbols per signal you're writing down will be an approximation of this, with the Q there. Now what you expected to get was this. Right? When you bought PX off the shady dealer in the probability market, this is what you thought you were promised. And then a third quantity is, well, what you could do if you really knew the true distribution. All right. And the KL divergence is the difference of two of these quantities, and that's its meaning. So recall the KL divergence is by definition the following sum
Is the reason I expected to get the second one because I thought
that's
P was
right.
optimal,
Yeah.
so it should
Well, you
say
thought P was the truth. Yeah. That's
Yep.
right. Okay, so that is the first term here was what you got minus what is optimal. And by what, I mean the number of symbols per signal, or really the number of symbols per like signal in a block as the block length goes to infinity, minus what you could do if you actually knew the true distribution, right? So i.e. the KL divergence is the gap. I mean, this is positive, right? Because you can't do better than the knowing the truth. You can always, in expectation, shorten the number of symbols you use to record signals if you know the truth, compared to thinking it's some other distribution. So it's the expected number you will save. So the expected number of symbols per signal. You save, as in you don't have to write down, by switching from your encoding based on P to an encoding based on Q. And from this definition, you can sort of see how Q and P play asymmetric roles, right? Okay, so that's it. That's the meaning of the Kale divergence from an information theoretic point of view. It's the expected number of symbols per signal you save by using an encoding based on the truth rather than your model, you could say, P. All right, so are there any questions?